Last class, we opened up the switch and saw how it moves data around within a single local network, delivering frames by MAC address. But that only works inside one network. Now think about what actually happens when you open a website hosted on the other side of the planet. Your request leaves your laptop, leaves your home network entirely, and somehow crosses dozens of separate networks and A212, your internet provider, backbone networks, the destination and 39, SAR provider, and A212 to reach a specific server thousands of miles away. How does it find its way? That is the question routing answers, and it is one of the most elegant ideas in all of networking. Routing is how packets travel between different networks, hopping from router to router across the world until they arrive at their destination. And the beautiful part is that no single device knows the entire path. Each router along the way makes just one simple decision, an A212 and A220, which weighs one step closer, A221 and A212, and from that repeated local decision, made millions of times across millions of routers, packets find their way across the entire internet. Today, you will learn what a router does, the routing table it uses to decide, the default gateway that handles the unknown, and how packets travel hop by hop. By the end, the magic of a request crossing the world will make complete sense. Let us begin. Here is our path for today. First, what routing actually is. Second, the router in T9's job. Third, the routing table. Fourth, the default gateway. Fifth, the hop-by-hop journey. And sixth, how routers learn their routes. Let us dive in. Let us start by placing routing next to switching, because the contrast defines exactly what routing is. Switching, from last class, operates within a single local network. A switch moves frames from one device to another on the same LAN, and it makes its decisions using MAC addresses and A212 hardware identities that only have meaning locally. Switching is local delivery, getting data from one machine to another when they are on the same network, in the same building. It knows nothing about the world beyond its own LAN. Routing is the level above. It moves packets between different networks, and it makes its decisions using IP addresses and A212, the logical hierarchical addresses designed precisely for identifying networks across the whole internet. Where a switch asks an A200 array, which port on my network is this MAC on? So the clean division is this. Switching is local delivery within a network by MAC. Routing is finding a path across networks by IP. When data needs to travel beyond its own local network and 8200 kist to another network to the internet and 8200 kist 200, routing takes over. Every time you reach something outside your own LAN, packets are being routed, hopping across network boundaries by IP address. Switching gets you across the room, routing gets you across the world. That is the fundamental relationship, and holding it clearly is the key to everything today. So the takeaway, switching moves frames within one local network by MAC address, while routing moves packets between different networks by IP address and A212. Switching is local delivery within a LAN, and routing is finding a path across networks, taking over the moment data must leave its own network. At the center of routing is the router, so let us be precise about what it actually does. A router is a device that connects different networks together and forwards packets between them. Physically and logically, it sits at the boundary and A12 wall. A router has a foot in two or more networks at once, and its purpose is to be the bridge between them. Your home router, for instance, connects your home network on one side to your internet provider, INT9's network on the other. Every router is a junction where networks meet and traffic passes from one to another through it. Its core action, performed for every single packet, is a decision. A packet arrives, the router reads that packet in Tinia's destination IP address and 84K Artholau, where it is ultimately trying to go and 84K Artholau, and then decides which of its connected networks, which direction, to forward the packet toward so that it gets closer to that destination. Read the destination, choose a direction, forward. That single decision made over and over, is the essence of what a router does. Notice the router does not need to know the full path to the destination in 8112, and this is the crucial simplification. It only needs to know which neighbor to hand the packet to next to move it one step closer. It is like asking for directions and being told an A2A1 head that way and ask again at the next junction on A2A2 Each router is responsible only for the next step, not the whole journey. This is what makes routing scalable to a system as vast as the internet. No device has to comprehend the whole. Each just knows its local piece of the puzzle and 85 and T124. Which direction is closer? How does it know that? Through the routing table, which is next. So the takeaway, a router connects different networks and sits at the boundary between them, and for every packet, it reads the destination IP and decides which direction to forward it next and 82 while it need only know the next step toward the destination, not the whole path. Which is what lets routing scale to the entire internet. How does a router know which way to send a packet? It consults its routing table and A2112, the map that drives every decision. The routing table is a list held inside the router of known destination networks, and for each one, the way to reach it and AT to fund, essentially, and D to fund, to get to network A, send the packet in this direction to get to network B. Send it that way. An 8 to a fee. It is the router on tiny eyes, knowledge of the world around it, expressed as a set of rules mapping destinations to directions. Every router has one, and it is the single source of truth the router uses to make its forwarding choices. Here is how it is used for each packet. The router takes the packet and CCNA's destination IP address, and it looks through the routing table to find the entry that matches which network that destination belongs to. When it finds the matching entry, that entry tells it the direction NA200 to A200, the next hop NA200 to send the packet. Match the destination to a known network, read off the direction, forward it that way. The routing table turns N8200. Where is this packet going N8200? Into N8200. Which way do I send it N8200 in a single lookup? The key insight is that a routing table does not need an entry for every individual device on the internet, and N8200 that would be impossible with billions of devices. Because IP addresses are organized into networks, the table works at the level of networks, not individual machines. One entry can cover a whole network of many devices. This is why IP addresses being hierarchical and AT200 twofold grouped into networks and OT200 twofold matters so much. It keeps routing tables to a manageable size, listing directions to networks rather than to every device on Earth. The routing table is the compact map that makes the router and T9 test job possible. So the takeaway, the routing table is the router and 39's map, listing destination networks and the direction and AT2fold, the next hop and AT2fold to reach each. For every packet, the router matches the destination IP to a network entry and forwards accordingly. And because it works at the level of networks, not individual devices, the table stays manageably small. The routing table raises an obvious problem. There are countless networks on the internet, and no router could possibly list them all. The elegant solution is the default gateway. No router can know about every network on Earth, NA212. There are far too many, changing constantly. So a router will frequently receive a packet whose destination network is not in its routing table at all. It simply has no specific rule for where that packet should go. Without a solution, the router would have to give up and drop the packet, which would make reaching most of the internet impossible. The default gateway is the answer. It is a special catch, all entry that says, in effect, NA200 200. For any destination I do not have a specific route for, send the packet this way. A200 200 200. It is the route of last resort. When a router looks up a destination and finds no matching entry, it falls back to the default gateway and forwards the packet in that direction and 800 12, typically toward a bigger, more knowledgeable router, and ultimately toward the wider internet. This is exactly how your own devices work. and it makes the idea concrete. Your laptop has a very simple routing table. It knows its own local network, and for absolutely everything else an 8 to high fall, every website, every server in the world an 8 to high fall all or it sends the packet to its default gateway, which is your router. Your router then does the same thing at the next level up. Each device only needs to know its local networks plus one direction for N8220, everything else N8021, and by chaining these defaults together, a packet with an unknown destination gets passed steadily upward and onward until it reaches a router that does know the way. The default gateway is what lets a device with almost no knowledge of the internet still reach any part of it. So the takeaway, because no router can know every network, the default gateway is a catch-all route of last resort and A2012 and A2020 for anything I have no specific route for. Send it this way in 8280N, 8212, so your laptop knows only its local network and sends everything else to its gateway. And chaining these defaults upward lets a packet reach any destination. Now let us follow a packet on its actual journey across the internet, because seeing the whole trip ties everything together. It begins on your device. Your laptop wants to reach a distant server, sees the destination is not local, and sends the packet to its default gateway NA212, your home router. That is hop 1 from your device to your router. Your router looks at the destination, finds no specific route, and forwards it to its own default gateway and AT112, your internet provider and 39 network. Hop 2. The packet has now left your home entirely and is out in the wider internet. From there, the packet passes through router after router and AT112, your provider and AT109, 6 routers, backbone routers that carry huge volumes of traffic between regions. Then the destination provider AT109, 6 routers. At each hop, a router receives the packet, reads its destination IP, consults its routing table, and forwards it one step closer, and A224. Sometimes via a specific route it knows, sometimes via its default gateway door that knows more. Each router handles just its one hop, its one decision, and passes the packet along. The journey is a relay, not a single leap. Finally, the packet reaches a router that is directly connected to the destination at tiny network. This last router recognizes the destination network as one of its own, and it delivers the packet onto that final network to the specific server. The journey is complete and A125, and remarkably, no single router along the way ever knew the entire path. Each one knew only its next hop. The full route emerged from many independent local decisions, each router contributing one step. That is the profound elegance of routing, a globe-spanning path, assembled hop by hop, with no central map and no router needing to understand the whole. From simple, local rules, worldwide reach. So the takeaway? A packet travels hop by hop, an A212 from your device to your router, to your provider, to backbone routers, to the destination at 39, S network, and A212, and at each hop, a router reads the destination, consults its table, and forwards one step closer. No router knows the whole path. Yet the full global route emerges from each one and tiny gas, single local decision. Let us zoom in on that repeated decision, because its uniformity is what makes the whole system work. At every single hop, every router does exactly the same 3 things. First, it reads the destination IP address of the packet and A212, the N822. Where is this going A21 mine that never changes as the packet travels? This is the router inputting 9S input, the goal, stamped on the packet from the start. Second, it looks that destination up in its own routing table, finding either a specific matching route or falling back to its default gateway. This is where each router applies its own local knowledge of the networks around it. Different routers have different tables and 8-head wall. A backbone router knows far more than your laptop and 8-head wall. But the lookup step is identical in kind, matches the destination to the best known direction. Third, it forwards the packet out toward the next hop that the lookup selected. then it is done with that packet entirely in AT4. It has played its one part, moving the packet a single step closer, and the next router will repeat the process. Read, look up, forward. That is the complete, uniform decision, performed identically by every router on Earth, billions of times a second. The power of routing comes precisely from this simplicity and uniformity. Because every router follows the same tiny procedure, they interoperate seamlessly, and packets flow across countless independently operated networks as if it were one system. A simple rule, repeated everywhere, produces global connectivity. So the takeaway, at every hop a router performs the same three steps, and A212, read the packet in 339, S destination IP, look it up in its routing table, or fall back to the default gateway, and forward toward the chosen next hop, and A212. And because every router on Earth follows this identical, simple procedure, they interoperate seamlessly to carry packets across the whole internet. One question remains: where do all these routing tables come from? How does a router come to know the directions it stores? There are two ways. The first is static routing. A human administrator configures routes by hand, manually telling the router and A220 to reach this network, go this way, and A220. Static routes are simple and predictable, and they are fine for small, stable networks where the layout rarely changes and there are only a few routes to maintain. But they have an obvious weakness. If the network changes, an A212, a link goes down, a new network is added, and A212, someone has to manually update the routes. That does not scale, and it does not adapt to failures on its own. The second way is dynamic routing, and it is what makes the internet possible. With dynamic routing, routers automatically share information with each other about the networks they can reach using routing protocols. They essentially talk among themselves: any A212, any A220, I can reach these networks. What can you reach? A200, 200, 220, any A200, 200. And from this exchange, each router builds and continuously updates its own routing table. Crucially, when something changes, an A212, a link fails, a new path appears, an A200, 212, the routers learn about it and adapt, rerouting traffic around the problem automatically, with no human intervention. This ability to learn and adapt is why dynamic routing scales to the entire internet. No human could possibly hand configure the routes for billions of devices across millions of constantly changing networks. Instead, the routers collectively figure it out and keep it current, healing around failures and incorporating new networks on their own. So static routing is the manual, simple option for small, stable setups, while dynamic routing is the automatic, adaptive engine that runs the global internet. Together, they cover the spectrum, but it is dynamic routing N39, self-organizing intelligence that lets a system this vast and ever-changing simply work. So the takeaway? Routers fill their tables two ways: an A212, static routes configured by hand, simple but manual and fine, only for small stable networks. And dynamic routing, where routers automatically share reachability and adapt to changes, and A222 how. And it is dynamic routing and self-organizing, self-healing intelligence that scales to run the Internet of Go. Before we recap, here is a way to witness everything we have discussed with your own eyes, using a tool built into virtually every computer. The tool is called Traceroute and 8212, or Tracert on Windows and 8212, and it reveals the actual sequence of routers a packet passes through on its way to a destination. You give it a destination, like a website, and it reports back each hop in order: the first router, the second, the third, all the way to the target. It is a live window into the hop-by-hop journey we just described, no longer abstract but shown as a real list of the machines your packet actually traversed. Running it is genuinely illuminating. Trace a route to a server on another continent, and you will see the packet leave your router, pass into a provided NES network, cross several backbone routers NE820. Often you can guess the cities from their names NE820, enter the destination provider, and finally arrive. You're watching routing happen. Each line is one router making its one decision to pass your packet along. The abstract idea of an 820 hopping across networks and 821 becomes a concrete, numbered path you can see and count. It is also a practical diagnostic tool, which is why network engineers reach for it constantly. If a website is slow or unreachable, a traceroute shows you how far your packets get and where the journey breaks down or slows an 812 fall. Is it near you, in the middle of the internet, or close to the destination? By revealing exactly where along the path a problem lies, traceroute turns awake an IT 200. The internet is broken an 8200 into a specific locatable fault. In today, in 1939 SEM lab, you will run traceroute to a few destinations and read the hops yourself, an 830A2 the best possible way to make routing real. Seeing your own packets cross the world, router by router, is the moment this all clicks. So the takeaway, the traceroute tool reveals the actual sequence of routers a packet passes through to reach a destination, turning the abstract hop-by-hop journey into a concrete numbered path you can watch and add 2008-12. And because it shows exactly where a path breaks or slows, it is both an illuminating demonstration and a practical everyday diagnostic tool. Let us gather the whole class in one breath. Routing moves packets between networks by IP address, where switching moves frames within one network by MAC. A router sits at the boundary between networks, reads each packet in 39's destination IP, and forwards it onward. The routing table is the router in 39's map, listing destination networks and the direction to reach each. The default gateway is the route of last resort, an 8200 toll, where to send anything with no specific route. Packets travel hop by hop, each router moving them one step closer, none knowing the whole path. And routes are learned statically by hand or dynamically by routers, shading and adapting an 8202 fall, which scales to the internet. Namaiti, next class an ATN12 DNS, turning names into addresses, one idea at a time. That is routing an